So hello everyone, I'm Victor Kreuzfeld from the University of São Paulo, and in this video I will present our accepted paper in ICC 20, more specifically in the workshop on scalable massive MIMO technologies for beyond 5G. Our paper is entitled as Low Complexity Distributed XL-MIMO for Multi-User Detection, and is the result of the cooperation of three universities. First, the Laboratory of Communications and Signals of University of São Paulo in Brazil. Then we have the Connective Group of Aalborg University in Denmark. And last, the Laboratory of Telecommunications and Signal Processing of State University of Londrina, also in Brazil. We divide the presentation the following way, where our main goal today is to explain the problem that we are working on and introduce qualitatively the most important conclusions that can be taken off from this paper. Well, our focus remains on extra-large MIMO, also called as XL-MIMO, which can be thought of as a natural extension of the well-known massive MIMO. The fact is that XL-MIMO can be a very important way to increase communication coverage and data rates in the near future by taking advantage of, for example, building and stadiumificates to assemble large antenna arrays. The idea is that when we increase too much the number of antennas at the base station, new channel effects emerge, which represent new challenges in how the networks operate. The main important effect that we are interested in is no stationarity. And also we are focused on studying the detection of the signals sent by the users towards the base station in the uplink phase. So here is the system architecture that we are adopting, in which we have a very large uniform linear array divided into fixed and smaller arrays called as subarrays. Each subarray has its own LPU, and the control and exchange of information is carried out by a CPU. No stationary effects can be translated into the concept of visibility regions, which are represented in this toy example here. Due to large extension of the array and the near proximity of the user to the array, the energy sent by each user is concentrated only in a small portion of the array. Therefore, not every antenna attends all the users, and we can say the same thing to the subarrays as well. It's important to note that some visibility regions can be overlapped, like this one here, which trivially gives rise to interference among users. So the key idea here is to note that a set of antennas do not need to be activated on a given communication stand. We basically want to exploit this notion to save energy when perform signal detection. The main problem with classical massive MIMO receive combining schemes like regularized zero forcing applied on a subarray basis is that we cannot exploit straightforwardly the physical consequences of visibility regions. This leads to high computational complexity, that is high energy consumption, basically, and an inflexible way to deal with the problem that we are trying to solve. So the goals of this work are and were to find a low complexity receive combining scheme which can be performed in a distributed manner and can properly exploit the notion of active antennas, which emerge due to no stationarity effect. In this way, we are able to reduce cost and complexity of the hardware employed in LPUs and the CPU. We can also reduce cross-communication between CPU and LPUs and increase the efficiency and flexibility of the network as a whole. So one appealing and already know low complexity signal detection method for massive MIMO is based on the randomized Cox-Marks algorithm. Then our idea was to extend it to the context of XL-MIMO and study if we can achieve our goals with it. In particular, the randomized Cox-Marks algorithm is an iterative method envisaged to solve systems of linear equations, where randomization provides us with some convergence guarantees. We apply the algorithm to resemble the performance of RZF. And it is relevant to emphasize that the main characteristics of this method in particular are its simplicity, since only the number of iterations needs to be turned, and the fact that we can easily trade performance and complexity by adjusting this unique parameter. Here is a diagram that represents the main steps of the receive combining scheme based on the randomized Cox-Marks algorithm. For each subarray, we go through all the antennas that have relevant power, all the users that have a relevant power, and do the core steps related to the Cox-Marks approach, which are these ones here. After reaching a desired SR, I, and R performance level, the algorithm outputs the received combined vectors of the users served by the subarray, which is again an estimated version of the RZF. So the different test randomization schemes are the following. First, the power-based, in which users with higher energies are more often selected. Then we have in second position the uniform, wherein our users have the same probability of selection. And the third one, in which the probabilities are based on the number of active antennas of each user. Note that these probabilities are related to the equation selection when solving the SLE that resembles the RZF scheme for each user. I'm not entering so much detail here, but this is the basic idea behind the algorithm. This is a diagram that represents the operation of our XL-MIMO network. Observe that its subarray estimates the RZF receive combining matrix via the algorithm, and then it computes the estimated received signal. These signal estimates are sent to the CPU, where they are fusioned by using the DLDF algorithm. Well, recall that this fusion operation is needed because the same user can be served by different subarrays. This DLDF distributed linear data fusion method was proposed by this paper here, and we are applying in the CPU to collect the results. Now I will present our main findings, where this graph here shows the average computational relaxation degree of our algorithm to the canonical way of computing RZF as a function of the noise variance. So the SNR is increasing towards the left side of the graph. We have found that our algorithm is less computationally burdened than RZF, even now with no stationary effects. So we are extending the conclusions draw for massive MIMO. And well, we can also easily trade performance by complexity and vice versa. As we can see here, where these top curves consider a losing of 10% of R0, RZF, SI, and R. And those ones further down are losing of only 1%. So note this gap here and how the relaxation degree decreases as we increase the performance of the algorithm. And also observe that we get better results on average for uniform randomization, which is given by the blue lines. At last, we observe that when the overall SNR is large, the algorithm performs worse since we have a higher interference level among users. So this side of the graph here. To sum up, receive combining schemes based on the randomized Cox-Marx algorithm are a promising approach in the context of XL-MIMO, since we can exploit the idea of active antennas. It works well in a distributed manner, and we can obtain high computational complexity gains, mainly when the number of both antennas and users are very large, which corresponds to our scenario of interest. In particular, we also have found that the uniform randomization approach is the best in terms of average performance, and that the active antennas randomization has some relevance when you stop thinking on average. For future work, we aim to do an energy efficiency analysis to better explain the complexity gains that we observed here. We also consider went to consider the spatial correlation among the antennas and user beams to evaluate a more realistic channel. And well, when to think about better ways to improve the performance of the algorithm by better exploiting the visibility region effects. And finally, better account for possible gains in the system as a whole. So this is it. Thank you for watching, and you can have access to the archive version of the paper by scanning the QR code on the left, and the simulation codes are also accessible via the QR code on the right. Have a nice day and goodbye.